In May 2013, a monster emerged from the Oklahoma plains, a vortex so vast it defied classification. Its swirling mass stretched an unbelievable 2.6 miles wide, becoming the largest tornado ever recorded. This wasn't just another storm, it was a meteorological enigma, an anomaly that caught every expert completely off guard. This behemoth moved with erratic, unpredictable speed, its multiple vortices dancing a deadly ballet. Its sheer scale dwarfed towns, swallowing horizons with a terrifying, silent roar. Researchers, armed with cutting-edge radar, found themselves staring at data that simply made no sense, pushing the boundaries of storm science. El Reno, a name now synonymous with meteorological shock, broke every scale, every assumption. It was a storm that did not just destroy landscapes, it dismantled our fundamental understanding of how tornadoes form, behave, and dissipate. This single event reshaped extreme weather research forever. On May 31, 2013, near El Reno, Oklahoma, meteorologists anticipated a severe weather day. However, nobody foresaw the historic event that would unfold. This region, part of Tornado Alley, is no stranger to powerful storms, yet El Reno transcended anything observed before. Its significance lies not only in its destructive power but in its revolutionary data. Mobile radar units, deployed by researchers, captured unprecedented detail inside the storm. This precious information provided a terrifying glimpse into a tornado operating on an entirely different scale. Before El Reno, our models for supercell tornadoes, while advanced, had limitations. They struggled with complex, rapidly evolving dynamics. Meteorologists believed they understood the upper bounds of tornado size and behavior, a belief that El Reno would violently shatter. The heart of Tornado Alley, a corridor stretching across the central United States, provides the perfect confluence of conditions for violent storms. Warm moist air from the Gulf, cool dry air from the Rockies, and a strong jet stream collide, creating volatile atmospheric instability. The morning of May 31 began like many others in late spring. But by early afternoon, radar painted a concerning picture, a powerful supercell developing rapidly southwest of Oklahoma City. Its trajectory pointed towards populated areas, escalating the sense of urgency. Initial radar readings revealed a storm unlike previous observations. Its mesocyclone, the rotating updraft at the storm's core, displayed an unusually broad and deep structure. This hinted at the immense scale of the impending tornado, though its full extent remained hidden. Experienced storm chasers, positioning themselves carefully, witnessed a monstrous, rain-wrapped funnel forming. Its sheer girth obscured the familiar cone shape, making it difficult to discern its true boundaries. Their radios crackled with disbelieving reports. The supercell underwent rapid intensification, a process meteorologists call explosive cyclogenesis. Within minutes, its updraft velocity skyrocketed, drawing in vast quantities of moist, unstable air. This fueled an already potent storm, propelling it into an unprecedented class. What truly baffled experts was the emergence of multiple, powerful subvortices orbiting within the main circulation. These smaller, intense tornadoes added a layer of complexity and extreme localized damage potential, defying standard models of tornadic structure. The discovery of its unparalleled width came much later, after meticulous analysis of ground surveys and high-resolution radar data. Its 2.6-mile diameter was not immediately apparent due to its rain-wrapped nature and the sheer scale of the event itself. Measuring its exact width involved a combination of mobile Doppler radar, ground-level damage assessments, and photogrammetry. Scientists painstakingly pieced together the puzzle, revealing a colossal footprint that rewrote the record books by nearly a mile. El Reno was not just wide, it was a wedge tornado, a phenomenon where the funnel is wider than it is tall. This characteristic makes them appear as massive blocks of rotating cloud and debris, obscuring their true form and making them incredibly dangerous to spot. The storm also generated incredible wind speeds. Mobile radar units recorded winds exceeding 295 miles per hour, rivaling the strongest tornadoes on record. This data, however, presented a unique challenge for classification on the enhanced Fujita scale. The heroes of this scientific revelation were the mobile radar teams, often operating dangerously close to the storm. Their specialized instruments, mounted on rugged vehicles, provided unprecedented, high-resolution data from within the storm's immediate vicinity. When the initial data streamed in, meteorologists were stunned. The shear scale of the velocity couplets, indicating extreme wind shear, was unlike anything they had ever processed. It became clear El Reno was not just large, it was fundamentally different. Inside El Reno's colossal circulation, chaos reigned. Not one, but numerous smaller, violent vortices spun independently, each capable of EF4 equivalent damage. These subvortices, like deadly dancers, made the storm's path incredibly unpredictable and destructive. One subvortex, captured by researchers from the University of Oklahoma, reached a staggering 295 miles per hour. This incredible speed, the fastest wind ever measured within a tornado, highlighted the extreme localized power hidden within the larger storm. These rotating subsidiaries, instead of merging, maintained distinct identities within the broader circulation. Their interaction created zones of extreme shear and turbulence, making El Reno a uniquely perilous storm for anyone caught in its path, including seasoned chasers. The low-level jet stream, a ribbon of fast-moving air near the ground, played a crucial role. It provided the necessary shear and moisture convergence, fueling the storm's rapid growth and sustaining its incredible intensity for an extended period. El Reno's mesocyclone exhibited an unprecedented, broad, and shallow structure compared to typical tornadoes. This wide base allowed for the formation and sustenance of multiple intense vortices, a key characteristic differentiating it from prior records. Baroclinic vorticity generation within the storm's outflow boundary added to its complexity. This process, where horizontal wind shear is converted into vertical rotation, contributed to the spawning of additional vortices along the storm perimeter, expanding its destructive footprint. The enhanced Fujita scale, the standard for rating tornado intensity, relies heavily on damage indicators. But El Reno's path, primarily through rural, unpopulated areas, provided limited structural evidence for a conclusive EF5 rating. Despite mobile radar recording EF5 equivalent winds, the lack of sufficient ground damage meant El Reno was officially rated EF3. This highlights a critical limitation: the scale measures damage, not simply raw wind speed, creating a disconnect in its full destructive story. The challenge of ground truth data collection was immense. The storm's rapid movement and rural track meant few structures were directly hit. Verifying the highest wind speeds required innovative techniques, relying heavily on the invaluable mobile radar data. Tragically, El Reno claimed the lives of 8 people, including 4 renowned storm chasers. Their pursuit of knowledge brought them too close to a storm that defied all expectations, a stark reminder of nature's raw, unpredictable power and the risks of scientific exploration. In the wake of El Reno, meteorologists developed new computational models. These sophisticated simulations now incorporate the complex multi-vortex dynamics observed, significantly enhancing our ability to predict similar, rare events. The storm's unparalleled width forced a re-evaluation of how tornado size is defined. Experts now consider not just the visible funnel but the entire circulation envelope, including the broad area of damaging winds, painting a more accurate picture of its true impact. The critical data from mobile radar units underscored their indispensable value. Investment in these cutting-edge instruments has surged, allowing for unprecedented, close-range observations that stationary radar cannot achieve. They are the eyes inside the storm. Forecasting has grown more precise, thanks to El Reno's lessons. Meteorologists now integrate broader atmospheric context with high-resolution models, offering earlier and more targeted warnings for large, complex supercells. Every minute counts when lives are at stake. Warning systems have adapted, emphasizing the potential for widespread, erratic hazards within large, rain-wrapped tornadoes. Public safety messages now stress the importance of understanding the storm's entire destructive footprint, not just the visible funnel. Public awareness campaigns educate communities about the unique dangers of these massive storms. They teach people to seek immediate shelter, especially when a tornado is rain-wrapped and its true size is obscured, potentially saving countless lives. The storm-chasing community, despite its losses, continues its vital work. Their brave efforts provide invaluable real-time observations and ground truth data that complement radar findings, pushing the boundaries of what we know about these formidable forces. understanding tornadic environments has deepened. Scientists now better grasp the precise atmospheric conditions required to foster such colossal storms, allowing for more accurate long-range predictions of severe weather outbreaks. Future predictions suggest that while rare, El Reno-type supercells might become more common under changing climate conditions. Research continues into the subtle shifts in atmospheric dynamics that could lead to more frequent occurrences of such extreme events. The potential connection between climate change and the intensity of severe weather is a crucial area of ongoing study. El Reno serves as a stark warning, urging scientists to accelerate their understanding of how a warming planet might influence future storm development. El Reno forces us to confront our humility in the face of nature. Despite our advanced technology and scientific prowess, the Earth's dynamic systems can still produce phenomena that transcend our comprehension, reminding us of our fragile place. The relentless pursuit of knowledge, even in the face of immense danger, defines human progress. The data collected from El Reno, at such a high cost, represents a monumental leap in our understanding, fueling new questions and inspiring future generations of researchers. Ultimately, every discovery about storms like El Reno serves a singular, profound purpose: to protect human life. Better predictions, improved warnings, and greater public awareness all contribute to saving lives when nature unleashes its rawest fury. The terrifying beauty of a supercell, the raw power of a tornado, evokes both fear and profound wonder. El Reno stands as a testament to nature's capacity for both breathtaking majesty and devastating force, a spectacle of the atmosphere itself. Our relationship with extreme weather is constantly evolving. As we gain deeper insights into phenomena like El Reno, we learn not to conquer nature, but to respect its power and adapt, building more resilient communities and a safer future. The El Reno tornado of 2013 remains a monumental turning point in meteorology, a ghost of the plains that redefined our understanding of extreme weather. Its lessons continue to resonate, guiding our quest to unravel the secrets of the sky. What aspects of El Reno's story fascinated you most? Share your thoughts in the comments below. If this journey into extreme weather captivated you, please like this video, subscribe for more in-depth documentaries, and join our community of curious minds.